what I'm going to do now is finally what I care about is using this photonic crystal for squeezed light generation. So the crystal is going to be made from a nonlinear material which will produce squeezed light, and the material will be some type of will have some type of structure that will enhance the nonlinear generation. Okay, so we should be able to create, this is the squeezing operator, multi-mode squeezing operator. So if we just search for multi-mode squeezing operator, they don't have a free version of this. Do they have an archive? Whatever, I'll try this one. General multi-mode squeeze states, okay. Yeah, something like this. So essentially it's a sum over I and j, but since we are assuming a continuous spectrum, then we have integrals, and you just take the creation operator for two modes, mu and nu, and so you do. So if it's single mode squeezing, then mu and nu are the same, and if it's multi-mode, then you have different combinations of mu and nu. And I think what this means, what it does mean, is that you're going to create two photons, one with frequency mu and one with frequency nu. And then you're summing over all possible frequencies. But you're always creating pairs of photons. Alright, and so this is written in terms of A daggers, which are the true modes. They're the modes which satisfy Maxwell's equations, and they have real frequencies. And the modes are eigen states. So we could start in vacuum. Let's say. And let's assume there's no light in our crystal. We're just in the vacuum state. Yes. Then, but just to finish that thought, I could apply the squeezing operator to the initial vacuum state, and it would tell me what the state would be. It would give me a squeezed vacuum state written in terms of the true modes. But whatever. So what I wanted to look at was spontaneous. Alright, so is there something here? Hamiltonian Hamiltonian 2 is 29, page 29. Four-wave mixing. Yes. It's gonna be something like that. I mean, I don't like. It's not detailed enough. Actually, I can probably. Why can't I just find a good source? Whatever, but hey, whatever. Okay, the point is that some Hamiltonian gives rise to this squeezing operator. The whole point of that is that what I want to say is that the squeezing parameter psi, whatever this is, will depend on the interaction strength and the pump amplitude, and whatever else. So this parameter psi is what is C? Parameter C will be dependent on the modes of the structure. Okay, so if we knew what those modes were, then we could evaluate the squeezing operator on the vacuum. But the whole point of this project is that we don't know what those modes are. We know what the quasi-modes are. So in order to determine the squeezing operator's action on the vacuum, we need to write this in terms of the quasi-mode operators, the projected squeezing. So we need to project the squeezing operator onto the quasi-modes. So in order to do that, I have to sandwich the squeezing operator between the two projection operators. And initially this seems like a very complicated thing to do because if I expand this exponential operator in a Taylor series, where sigma is just whatever's in the exponent, then it looks like at first glance that I have to project every power of that argument. So I have to project sigma, then I have to project sigma squared, so on and so forth, up to sigma to the power infinity. So just carrying this out here, what I'd have to do is find some type of pattern and write the projection of sigma to the k in some general sense. That's difficult to do in general. So instead, let's consider this projection instead. So let's just see what happens if I take the exponential of the projection of the logarithm of s. So if I take the logarithm of s, sigma comes down, log e cancels, gives me 1. And so this just becomes sigma, which is what I've written on the right-hand side here. If I expand this in a Taylor series, I've effectively factored out or taken out the k. So this is what it looks like when I expand it. So I get, the first term I get is oh, my bad, that should be a 1. That should be a 1 there. Let's see if that fucks me over. Okay, so when k is equal to 0, I just get 1. Anything to 0 is 1. Plus p sigma p plus 1/2 times p sigma p times p sigma p, and so on. Now I'll use the fact that p times p is just equal to p. So all of these terms in the middle just become p. Alright, and that's all we can do there. Okay, so moving forward. Okay, so this is the point here. So if I could work out what this commutator was, if I have p times sigma, if p and sigma commute, then I can write this as sigma p, right? I can just flip it because the commutator is 0. And then I'll get p sigma sigma pp, but pp is p, I get p sigma sigma, which means I can pull the two p's to either side, and everything will be fine, as you'll see, because I'll get a sigma squared, sigma cubed, sigma to the power 4, all that inside of p's on both sides, and then it's equivalent to this, so then you can prove that e to the p sigma p is equal to the same as ps p. So we want to know the commutator. So let's define the commutator as some operator f, right? F is equal to p sigma p. And then we'll apply, we'll project f in this way. We'll sandwich it between two p's. We'll just do the same thing on the right side. And we just expand this commutator, so we'll get a p sigma minus sigma p, all of that times p, so we'll get a p squared sigma p minus p sigma p squared. Now we can write the p squared as p, or we can write the p as p squared. Nothing wrong with doing that. If we write it in this way, then we can bring the p's on the outside, and on the inside we just get sigma p minus p sigma, but that's nothing more than the commutator between sigma and p. Okay, so if we compare lines 229 and 225, they are the same, right? Except we must have that p sigma is equal to sigma p. Or I guess the way that another way to look at it is if I apply the inverse projections. If I do a p inverse times p, I get an identity. Do p times p inverse, I get identity, and then the same thing on this side. I should find that the operator f is equal to sigma p. And then if you compare the first to last line, p sigma is equal to sigma p. But this is only true if p sigma is equal to 0. Okay, so the commutator is 0. That means we can flip. Yeah, but I guess one interesting thing is that I've made no assumption on what sigma is. So sigma is just any operator. And what this, I mean, I may have missed something. I may have done something really stupid. But what this seems to tell me is that the projection operator commutes with any operator. So the only thing I think the only fact I've used is that p squared is equal to p. Other than that, I don't think I've made any other assumptions. Oh, and also that p has an inverse. So I've made the assumptions that p squared equals p, and p inverse times p is equal to identity, which is equal to p times p inverse, or p inverse times p and p inverse times p inverse times p and p times p inverse is both equal to each other and equal to the identity. I think those are the only assumptions I've made. I don't know though. But hopefully this is true. I don't see why it's not true. But whatever. Okay, putting this commutator into line 223, we can flip the orientation of p sigma, so we get sigma p, and then we just get a p sigma sigma p. And of course, these, yeah, I think I actually fucked up a bit. Yeah, I fucked up a little bit. Because that's actually equal to 1. Okay, so there's still a little bit of work to do. Because so my mistake originally, my mistake was this was either p times p here, where it should have been a 1. So I've just corrected that, and now it's gonna fuck up my results a bit. So I'm not as confident as I was at the beginning. But we'll try to work the equations here, and we'll see what we get. All right. So this is the thing that we want. Right. Okay, and then this is PSP. This is kind of a weird. No, this is. I don't know. This feels weird, doesn't it? Okay, so what if instead of doing P sigma P, what if we did something else? What if we had P sigma P? I think that's fine. Oh. So we have to prove. Okay, so we have to prove does the projection on A plus B equal projection? Linearity. Is a linear operator. How can I prove this? So if I put So prove one projection. Okay, so okay, so I guess it's linear. Okay, so when we project b plus 1, we get u. Well, probably, okay, a simpler way to see it is just to look at how our projection operator is defined. So, oh my fucking god. When does it ever end? Okay. Here. This is the projection operator. It's a sum. And it's these cats, right? So, if I have the inner product of operator A plus operator B, that's the inner product of A plus the inner product of B. So we're fine. It is a linear. We have is linear.
Yeah.
Where we have used the fact that P is linear, and I'll just put this. So if you just assume okay, so if you assume that P squared equals P, that's a projection operator, and you assume that that operator is linear and it has an inverse such that P inverse times P is equal to 1, then everything follows. How does this make sense? Let's say that sigma was equal to 0. Then S would be equal to the identity, and I would just get P squared equals 1 minus 1, which is 0, times equals P. Now, let's say that sigma was equal to identity. Then, good, yeah, so then E to the P if sigma is equal to identity, this is just P, so I just get E to the P. Okay, so if sigma equal to 0, then we have then 1 equal to 1 minus hat p if equal to 1, then what? E, this is P times E. This is P times E. Exponent problem missing. If equals 1 plus e to the p 1 plus p times e. Just get p times 1 over 1 plus 1 over 2 factorial plus 1 over 3 factorial. So PSP is just p times e. Give me 1 plus p squared S, if e is equal to 1, what is e to the 1? It's just e. No, it's 1 plus p times e minus 1. Equals 1 plus times e So if sigma equals 0, then we have identity equals to 1 minus p plus p squared. So this just gives me 1 minus 1 is 0. To get p squared equals p. Okay. If sigma is equal to identity, then we have the exponent of p is equal to 1 minus p plus p times the exponent of 1. So this, but if I expand this exponent and get 1 plus p make it 1 plus p times the exponent minus 1, because I have the sum from 1 to infinity. And this is equal to 1 plus p exponent 1 minus p. Okay, so at least in those two limits, the equation is true. Now, what if I didn't have these parts here? If sigma was equal to 0, if I didn't have this 1 minus p here, what would I have? So sigma is equal to 0, then I would have 1 is equal to p squared, which is not true. So you need this extra piece. So, okay. Okay. So, um, uh, okay, I'm just staring at this. I'm just thinking. What am I thinking? Basically, nothing really. I'm thinking of piano. Okay, back to work. So, all we have to do then is work out the projection of the pairs of equation and annihilation operators. And then sub these into here. Alright, so probably later today I'm gonna go eat breakfast. Later today I'm gonna make a video on actually doing this, so working out these projections, and then we will see what this projected squeezing operator looks like, and we will go from there.